So this gives us a very general idea about the nature of these single qubit gates, and it indeed emphasizes that they are continuous. In particular, the rotation angle phi is arbitrary, and also the rotation axis n can point into any direction in space. But in practice, we will only need a few very special cases, and these I'm going to describe now. So these are some very specific or special examples, and these are really the manifestations of these very general gates that we really need in practice. First of all, we realize that the Pauli matrices X, Y, and Z themselves are not just Hermitian matrices, but they are indeed also unitary matrices. So whenever we multiply one of these Pauli matrices by its Hermitian conjugate, then we can first exploit that these are Hermitian matrices, so this Hermitian conjugation doesn't really matter. So we simply have squares of these Pauli matrices, but we have exploited many times before that this is simply the identity matrix. And this is, of course, the definition of a unitary matrix. So X, Y, and Z are three of the most important single qubit gates. Indeed, we will soon compose these gates into more complicated ones by simply applying them consecutively. And as Y can be written simply as I times X times Z, we don't really need Y as well, so we will focus on X and Z. Well, let us see what these matrices are actually doing. Well, applying X to one of our computational basis states such as 1, 0, we just obtain the other one. And this works into both directions. Now, in terms of information, this is really transforming the state 0 into the state 1 and the state 1 into the state 0. So this can be naturally interpreted as a NOT gate. And the state Z is going to just leave the first basis state untouched, and the second basis state will just pick up a minus sign. This does not change the probability to find the qubit in the state 0 or 1, but it can be useful to change constructive to destructive interference. But in order to see such interference, we need superpositions. And what we see from these expressions is that these gates are not enough to bring our computational basis states into a superposition. For this, we just need one more extra gate, the so-called Hadamard gate. And this works as follows. This Hadamard gate is simply bringing our first computational basis state into the even superposition. So in terms of vectors, we can simply write it like this. And the second computational basis state is brought into the odd or antisymmetric superposition. It is useful to write this actually also down in Dirac notation. So the state 0 will be transformed into this superposition with a plus sign at this point, and the state 1 will be transformed into this superposition. Now this is enough to fix this matrix, so we can actually read it off from these expressions. And this can be done in several ways, but let me explain it in terms of a truth table. So as I said before, the truth table for a quantum system would simply look what happens to the basis states. So here we get these results as stipulated. And as I said, this is really just a representation of the matrix, so the coefficients that we find in front of these basis states are just our matrix elements. Recall that in this table, the matrix elements are organized as in the transposed matrix, but here the matrix is symmetric, so we can read it off directly. So therefore, expressed as a 2 by 2 matrix, this Hadamard gate has the following form. So there are 3 matrix elements, just 1 over root 2, and one which has an additional minus sign. So this is one of the key gates in quantum information processing, maybe even the most important one, and it is known as the Hadamard Gate. There are just two more gates that we will need, and they will only appear very occasionally, so I just mentioned them here already for completeness. And this is the so-called pi over 8 gate T, which is just a diagonal unitary matrix with a 1 on 1 on the diagonals and a certain complex number on the other diagonal. And the so-called pi over 4 gate S, which is a similar diagonal matrix, but simply now with I in this lower right entry here. So these are all the single qubit gates that we need in this course, and it can indeed be shown that any of these continuous single qubit operations can be well approximated by combining these ones here. And furthermore, as I emphasized, what we really need for most of the time are only the Pauli X gate, which is like a NOT operation, the Z gate, which changes interference, and the Hadamard gate, which brings our computational basis states into these superpositions. So often enough we will simply use the corresponding 2x2 matrices. We can also represent them graphically, as given here, and sometimes we use truth tables as indicated for the Hadamard gate. So we had three really important single qubit gates, which is already quite a bit more than just a NOT operation in a classical computer, and hence we should be perhaps worried that we need many more of these operations when we turn to the analog of binary gates, namely 2 qubit operations. But what we really need is just a single one of these. And this is the so-called controlled NOT gate. So our general expectation is that we need some pretty arbitrary black boxes that can transform any 2 qubit state into another 2 qubit state. But in practice we really only need one of them, and we best specify this by a truth table. So we start out with all the possible computational basis states. And we specify that these are going to be transformed in analogy to our classical controlled NOT operation. So this was this gate which we represented in the following way, where we have a control bit. This is our first bit that changes the state of our second bit, but only if the control bit is 1. And now we simply apply this to our basis states. So in the first two cases, where the first entry here is a 0, we will not change the second entry. But when the first entry is 1, then this 0 becomes a 1, and this one becomes a 0. So we just get this interchange of these two basis states here. So these are these two basis states, but just interchanged. So this is our C0 gate, which now of course is an operator. Generally this operator will act on a superposition. So we start out with a superposition in the computational basis with coefficients alpha, beta, gamma and delta. And then applying this C0 operator, we simply obtain a state in which these two coefficients have been interchanged. And from this we can read off how this looks like as a matrix, because this simply corresponds to the matrix that interchanges the last two entries of a vector. So this is the following matrix. Essentially a permutation matrix that interchanges the two last entries of a 4-component vector. We can also write this in a convenient block form, where we simply have an identity matrix and a Pauli X matrix on the diagonals and 2x2 zero matrices on the off diagonals. And this has a very natural interpretation when we consider how this acts on our state of 2 qubits when we write it in terms of two subvectors, phi0 and phi1. Phi naught is indeed the state of the second qubit when the first qubit is in the state 0, and phi 1 is the state of the second qubit when the first qubit is in the state 1. And when we then multiply this by the block matrix, then this simply becomes the following vector: phi naught and x times phi 1. So the state of the second qubit has not changed when the first qubit is in the state 0, but we effectively applied a NOT operation onto the second qubit when the first qubit is in the state 1. Later we are going to encounter this gate also in systems with more than 2 qubits, so it is useful to introduce a notation that tells us which of the qubits is a control qubit and which is a target qubit. And because of this, I'm going to call the matrix here specifically C12. So the first entry here simply specifies which qubit is a control qubit, here just our first qubit. And the second entry specifies which qubit is a target qubit, and here it's just our second qubit. So this is the only 2-qubit gate that we really need. In particular, along with our single qubit gates, this will already be enough to create entanglement.